So we're getting into the two-sample hypothesis testing today here in lecture 10 out of 12. So it's been a long time coming to get to what are probably the most common tests that you're going to do, with lots of build up to it. But the good news is it's the same principles. There's just some slight differences in the formulas, but all of the principles that you've learned, they're really going to do you well for moving into the two-sample hypothesis testing. So we've learned about using the normal Z distribution and the T distribution for one samples, and using the normal distribution for proportions, and we're going to continue and cover all of those things again today for two samples, as well as looking at this at the paired tests for dependent samples. And all of this is covered in section 5.4 of your textbook. So since it's been a little while, the original sequence of this course actually had this lecture coming immediately last week, but I moved ahead the chi-squared test and contingency tables to last week, just because many of you are using those for your project and I wanted to move them ahead. But logically, this is really a continuation of what we were doing 2 weeks ago and immediately before that. So I'm going to review it a little bit just to get it back fresh in your minds. So I want you to recall the work that we did on building confidence intervals, and also remind you a bit about the hypothesis tests. So the confidence interval, you'll remember, is our best estimate. Well, contains both our best estimate and our estimate of the uncertainty in a population parameter. So something like the average age of people in a room, the average age of people's guesses of someone's age. So there's something in the population which is a fixed parameter, but we only have limited information about it because we only have a small sample up from the population to make our estimate from. So in building a confidence interval, the mean from our estimate, or the proportion from our estimate, always forms the middle of the confidence interval. So in the first example, using the normal distribution, this is what we use when we know the standard deviation from the population. We're not having to estimate it from the sample. And to construct the confidence interval, we took the mean estimated from our sample plus or minus the critical value for Z given the confidence interval that we want. So for a 95% confidence interval, that's an alpha of 0.05. And we would look up the value of Z for 0.05 over 2, or 0.025, and multiply that by the standard error. And this component here on the right, remember what that was called? The margin of error. Yep. So it's the sample mean plus or minus the margin of error. And then when we introduced the T distribution for when we have to estimate the standard deviation from the sample instead of knowing it from the population, and when it's estimated from the sample, then we use T for that same critical level, but then you also need to know the degrees of freedom. And you all remember, so I just told you, but when to use T, when to use Z?
Use T for small samples, and, when you don't have the population standard deviation, you have the sample standard deviation.
Yeah, that latter thing is the key, really. When you have to estimate the standard deviation from the sample, then you use the T distribution. If you have a really large sample, like hundreds, then the T distribution and the Z distribution are almost identical, but you're still using the T distribution. It's just that they look almost identical. So use the T distribution when you have to estimate the standard deviation from your sample. And the issue is that when you estimate t from your sample, then or the standard deviation from your sample, then you have additional uncertainty in your margin of error. So it just expands your confidence interval a little bit more. But when it's estimated from a really large sample, then that expansion of your margin of error becomes negligible, and it's the same as z. Yeah, question. No. If it's a large sample, then it doesn't make much difference, but the key thing is whether your standard deviation is estimated from the sample. If the standard deviation is estimated from the sample, then you use t. So it's t that is correct for your sampling distribution. It's just that it becomes, for all intents and purposes, identical to z. For large samples, I'm not talking about n equals 30 here, I'm talking about n equals like a couple hundred, then it really starts becoming identical. And it matters what your value of alpha is too. If alpha is 0.05, then they become similar for not so large samples, but if alpha were 0.001, then it takes a much larger sample for them to be similar. But you just use t. Right? The key, the thing where sample size really matters with the t distribution is robustness to one of your key assumptions. Does anyone remember which one? Key assumption to using the t sampling distribution? Something about the population distribution. What's that? No, you don't need to make an assumption about the standard deviation, but you need to make an assumption about the form of the population distribution. Pardon? Yes, your sample has to come from a normally distributed variable. So if it's cholesterol, if it's age, it's some continuous variable, you're assuming that it's normally distributed. But once you get over n equals 30, you become extremely robust to that assumption, and it doesn't matter so much anymore. So that's where sample size really matters with the t-tests. It's not that you need to switch back to z or something when you get to large sample size. It's that you become robust to violations of your assumptions with large sample size. And that's an important thing to remember about the t-tests. You're assuming that you're sampling from a normally distributed population, but you become very robust to that assumption as you get to larger sample sizes. So then finally, we also built confidence intervals for a single proportion, and using the normal approximation to the binomial distribution, and using so the binomial distribution is well approximated by a normal distribution as long as your sample size is big enough and neither of your proportions are too close to 0 or 1. Then you can use this estimate of the standard error. So is everyone's memory of the confidence intervals pretty well jogged? All right, and confidence intervals and hypothesis testing, there's an equivalence between them in that you can use either one for these one sample tests, and you can use the confidence interval to do a hypothesis test, or you can do the hypothesis test using these steps where you calculate a p-value or a critical value of your test statistic and accept or reject your null hypothesis. And you come to the same conclusion as if you build a confidence interval and reject the null hypothesis if the population mean under the null is outside of your confidence interval, right? And in the realm of hypothesis testing, there are type 1 and type 2 errors, and then this idea of power. So if your null hypothesis is true, but you accidentally reject it, that's a type which error? Type 1. Yeah, that's a type 1 error. That's where there's nothing to be seen, but you think you see it anyways, or where you convict the innocent prisoner. The type 2 error is where there really is some difference. Your alternative hypothesis is true, but you fail to reject it because you don't have enough evidence. So you miss something that's there, or you fail to convict someone who is guilty. And power is if the alternative hypothesis is true, it's your probability that you will actually reject it. And there are these relationships between your study design and your type 1 error rate and the power. Of course, if you increase n, your standard error goes down, so your confidence interval shrinks, and your test statistic will increase, other things being held confident, so you get better power. If there's less variability in your population, so sigma, your standard deviation, goes down, your standard error will also go down, resulting in increased power. And increasing alpha, that decreases your power. By increasing alpha, which this is a little bit confusing here, what I mean by increasing alpha. So if you go from alpha equals 0.05 to alpha equals 0.01, does your power go up or down? Yeah, your power goes down because you need stronger evidence to be able to reject the null. So you're less likely to be able to do that. So I should probably note here by let's not call this increasing. I struggle with what to call that. How do you think of that? How do you describe, say, taking alpha from 0.05 to 0.01? Making alpha smaller?
Yeah.
Making alpha smaller, okay. Make alpha smaller.
What's the interpretation of an increase? Doesn't it make it stronger if you make it smaller?
Yeah, that makes so if you make alpha smaller, like you take it to 0.001, then that means your probability of type 1 error is smaller. So that means that you have stronger evidence for rejecting the null hypothesis.
Why do you say increasing? What made you?
Because it's increasing the significance level. So I guess that's why I wrote increasing. So making alpha smaller or increasing the significance level. And then finally, if you have more of a difference between the alternative hypothesis, if it's true, the more different it is from the mean under your null hypothesis, the greater power you have, because there's a bigger difference that you can see. Yes?
You mentioned this in the first section. You can always go back as power is 1 minus beta, right? Always saying that the probability of rejecting the alternative hypothesis.
Sorry, what's the question?
Which is the section no error probability is equal to no error probability is equal to power. That's by definition 1 minus beta.
Right, power is 1 minus beta. So beta is is if your alternative hypothesis is true, it's the probability that you fail to reject it. And power is the probability that you do reject it. So power plus beta is probability of rejecting plus the probability of not rejecting, which has to equal 1. Any more questions about type 1, type 2 error and power before we go on? I spend a lot of time on some of these things because I figure another year down the road, you're not going to remember much, but if you can remember some stuff like this, then I'll have done my job. And as I mentioned, the equivalence between hypothesis testing and confidence intervals. Here's a case. So here's the sample mean right in the middle of the confidence interval, and here's the mean under the null hypothesis. So in this case, do we reject or do we not reject the null hypothesis? Yeah, we reject. And here's an example where same sample mean, but we have a larger margin of error, maybe because there's a smaller sample size, maybe because the standard deviation of the normally distributed population is bigger, but we fail to reject. That other case where it becomes more difficult would be if the difference between the alternative and the null means were greater, but here that difference is the same, it's just the margin of error changing. This principle of equivalence, it's going to hold for 2 sample tests, but possibly not in the way you think. It's a common misnomer to incorrectly to translate this to the 2 sample tests in the wrong way. And I'll tell you what that wrong way is, but first I'll tell you what the right way is as we go through it. So we have 2 types of 2 sample tests that I'm going to talk about. There's the paired and the unpaired. So the paired or dependent samples test is when there is a natural pairing between your observations, and what you actually are looking at is the difference between those 2 observations. Okay, and the independent ones is where these are really not paired, they're just 2 independent samples and they need to be truly independent. I'll give you some examples of paired and unpaired tests. So some examples of unpaired tests. If we were to look at separate samples of boys and girls and were to compare the birth weights of them, that'd be, you'd use an unpaired t-test. Or if we had results from different participants in the clinical trial, so say from 2 different arms, your treatment, your control arm, that's unpaired. Or if you're going to take samples of households and how much they spend on healthcare in the US and in Canada, definitely unpaired independent samples. So in each of these cases, there's no relationship between your observations that you're comparing. Like they're separate individuals, they are independent. Maybe it'll make it clearer once I talk about some paired measurements. So if we were to take a set of subjects and first administer them a placebo and then put them onto a treatment and look at the difference in something about those patients before and afterward, that would be a paired measurement because we're looking at the differences in each individual. We were looking at ocular measurements, so measurements about the eye between the right and the left eye of the same subject. there's an obvious pairing, right? Stress measure scores in twins or husband-wife pairs. Now, the only way that it would make sense that we would want to do that is if there were some difference between those twins or husband-wife pairs. So say we take a pair of twins and one of them has been, I don't know, eating Twinkies since they were a child and the other one hasn't. And we find a bunch of twins where this is the case. And we want to do a direct comparison between the child who ate Twinkies and the child who didn't. That's a case where you would use a paired sample test. So the measurement from two methods of conducting an assay on a patient sample. So we've got one patient, two different ways of collecting a measurement, and we want to see whether the measurements from these two instruments are different from each other. Yes, question?
Would this be like if we're looking at the flu shot data and we're looking at the same population from this one survey, but then you say, did you get a flu shot and what is your race?
So the question is, so in the New York Community Health Survey, if there's a question about did you get a flu shot and what is your race? No, that is not a paired, that's not going to be a paired test because that is still just one individual and two different variables on one individual. So an example in the Community Health Survey that could be paired would be if you had, let's say households, and you wanted to say, are parents more likely to get the flu shot than their children are? So you're actually comparing within a household the parent to the children. That would be a paired test because those are two different individuals, but you want to keep them linked together. You don't want to just compare parents across the city to children across the city. Of course, there aren't children in this study, so we can't do that, but that would be an example of a paired test. And another key way of asking yourself, is this a paired test, is can I subtract? So can I subtract these measurements? So in the pre and post test on the same subjects, you could take your post-test result minus the pre-test result. Or if it's a proportion and you called one of the things, the yes is 1 and the no is 0, you could still subtract the 1s and the 0s. Ocular measurements, you can subtract what you measure for the two eyes. The stress measure scores, again, you can subtract. So in your example of flu shot and race, you can't subtract flu shot from race. It doesn't make sense. That's not a paired test. And I'll give you an example later, but the paired t-test is actually just a single sample test. So the independent samples, we're going to learn new methods for doing it as independent samples. But with paired measurements, you can actually just subtract them and then do your single sample test because you actually do a test on the differences, which is why that subtracting is important. Yes?
In that makeup, that case that you said, the two twins, one eats Twinkies, one doesn't eat Twinkies too. Does it always have to be a yes or no thing? Or they both eat Twinkies, or they both not eat?
So the key thing is that there has to be, like in the Twinkies, no Twinkies example, I was interested in, say, asking, is the body mass index of children who eat Twinkies different from those who don't? You need to have, and by doing a paired test, you're controlling for the large differences in overall weight of a family, you know, due to genetics and everything else that can occur, and you're just comparing between siblings. But unless you have one sibling who ate Twinkies and another one who didn't, then you have nothing to compare there. If you have two children who ate Twinkies, you can't say whether, based on that family, children who eat Twinkies weigh more than those who don't. So that has to do with it being a two sample test. There, the outcome variable, which for a t-test must be a continuous variable, would be weight or body mass index. Twinkies is more the grouping variable, where you get the, you know, what the thing that you're comparing against each other. Thanks for the questions. Okay, so here are some more questions for you. Which of these are paired measurements? If you wanted to compare the average heights of males and females. Unpaired. Good. To compare, of course, it's unpaired because we're just talking about, you know, individuals in the population. We're not talking about, you know, comparing what do you call those non-identical twins that are a boy and a girl. We're talking about men and women in the population, independent samples. To compare anxiety levels of individuals before and after an intervention. That's paired. Good. To compare anxiety levels in two groups, one with and one without an intervention. Yep, it's unpaired. They're different individuals. One group got the intervention, the other one didn't. And when there is a natural pairing of individuals like this, it's not just an option. You have to use the unpaired test because you're actually violating an assumption of the unpaired test. Do you know which assumption that is? Independence. Very good. They're not independent samples because it's actually the same group of individuals in both of your samples. So if you have this natural pairing, it's actually a good thing. It helps you to control for differences in the population that are not related to what you want to observe. So it's a good thing, and you must do it. Yeah, paired designs, it's a very efficient study design. You can observe what you want to observe and have good power with a smaller sample size by choosing a paired design. Because in the example of Twinkies versus no Twinkies, let's say, there's a huge range of body weights in the population, regardless of whether somebody eats Twinkies or not. So you're going to need a large sample to see whether there's a difference in the average weight of the Twinkie eaters or not. But if you are able to find, sibling pairs where one of them ate Twinkies and the other one didn't, in that pair, you're controlling for so many of the differences that occur in the population due to differences in upbringing, differences in genetics, and you are narrowing it down to a much smaller set of differences. So you're controlling for a lot of confounding, and you are controlling for differences that you would not otherwise be controlling. So it's a good design, but when you design a study that way, then you must analyze it as such. Make sense? Okay. Okay, so let's do some examples. The wonder drug aspirin, this was some data from an old clinical trial of aspirin and its effect on heart attacks. So this is a big study. We have 11,000 people each in the placebo and the aspirin arm. And that's important because the heart attacks were not terribly prevalent. So even though there are 11,000 people, there are only 189 people, a total of close to 300 people who had heart attacks. So yeah, first, what is the thinking of this in terms of a response variable and an independent variable? What's the response variable? What's that? Yeah, heart attack. So it's actually, it's a proportion, right? It's not a continuous response variable. So we're not going to use a t-test. This is just an example to talk about whether samples are paired or unpaired. It's not a t-test example. And the two groups to compare, they're, you know, whether the individuals were taking a daily placebo or a daily aspirin. And this is a randomized controlled trial where people were randomly assigned to take the placebo or the aspirin. This is pretty clearly an unpaired test, right? This, by the way, is a highly significant difference. But so we're going to set this up actually as a proportion. You could do this with a chi-square test, but you can also do it using a test of two proportions. We'll come to the same conclusion either way. So let's go through it. Let's set up the hypothesis. I'm going to show you how to do a two-sample unpaired test of proportions. Our null hypothesis here is going to be that the prevalence of heart attacks in the two groups is the same. So P1 equals P2, or P1 minus P2 is equal to 0. And the alternative is that they're not equal. We have a significantly large sample size, so we can go ahead and use the normal approximation to the binomial distribution, and we can do a z test. And of course, the data must come from a random sampling process. So going way back now to back when we did the test of one proportion, our test statistic, z, was the proportion in our sample minus p0, the proportion in the population under the null hypothesis, divided by a standard error, which was estimated as this under that normal assumption of the binomial distribution. And when we do it now for two samples, it's almost the same, except instead of p hat minus the population p naught, it's p1 hat minus p2 hat. So it's just a little bit of a modification. And the way that you calculate the standard error is a little bit different as well. So it's just a bit of a modification to your equations for z and for the standard error, but then you do it in the same way. And this equation for the standard error should give you a hint about how you're going to build a confidence interval. Okay, this is a tough question, but can anyone guess what the confidence interval will be centered around? Remember before it was centered around the proportion. When we have one sample and a proportion, the confidence interval, the middle of it was that proportion plus or minus the margin of error. Now, what's going to be in the middle of our confidence interval? Yes?
Is it like the difference in the proportion?
Exactly. It's the difference in the proportions. Great. And I'll show you that on this page too. But the p-value, you get something very small here, and we conclude that the proportion of heart attacks is different in the placebo and the aspirin group. So what is the 95% confidence interval? This 0.008 is the difference in those proportions, plus or minus the margin of error is calculated before. So this difference, the 0.071 minus 0.009, it's not a huge difference, but it's not a very high proportion either. It's a pretty big difference relative to those proportions. If we calculated an odds ratio here, it would be a fairly large odds ratio. So the middle of the confidence interval on this is the difference in proportions. Once you get into logistic regression, which we don't do in this class, but you can also build a confidence interval around the odds ratio, which is the confidence interval around the ratio of proportions. So you can also build a confidence interval or get your software to build you a confidence interval around the risk ratio or the odds ratio. And those are proportions of probabilities, whereas this is a difference in the probabilities. And that's an important distinction that we don't really get into in Intro Biostat. I get into it heavily in my Biostat 2 class and the Bios 1 class. I don't know if any of you will be taking it, but just how you can, in some types of models, be looking at a difference in proportions, and another one's a ratio of proportions. And you've now covered them both in this class, and I'll just tell you to keep in mind whether your software is giving you something about a difference or a ratio. The stuff you learned last class for categorical data analysis, those were ratios. This is differences. And they can both be interesting. You just have to know which you're dealing with. So that population difference is small. That's part of why often we would actually do this using an odds ratio, and because it tells you not just the difference in which can be small like this, but how much of an improvement relative to the proportion in your control group is, but because it can still be a big, this small proportion might still be important. And one of the things that I have mentioned before that is also a thing you should take from the course is that statistical significance and practical significance are not necessarily the same things. And you'd have to put this into context of public health in the population to determine whether it's practically important. But here a decrease of 0.01, so 1 out of 100 over a 5-year period, multiplied by a couple 100 million people, could be a difference in 2 million people having heart attacks or not. So the point is that even small proportions multiplied by a lot of people could be important. And that's a separate question to ask. So the confidence interval here and can still be used equivalently to the hypothesis test, just like before, but the confidence interval is on the difference in proportions. So you test whether 0 falls in that confidence interval. And if it does, then we can't confidently reject the null hypothesis that there's no difference between the two groups. Now, Can anyone guess what a common wrong way to use confidence intervals in an attempted equivalent way to the hypothesis test here would be with two samples? Maybe I shouldn't get you to think about a wrong way to do it, but it really is common. I've been told. I don't think it's common among students from my classes, but out in the world. So what if we were to build a, you know how to build a confidence interval for one sample, right? So you could just do it separately for each of these two samples. You could build this confidence interval for sample 1 and this confidence interval for sample 2. And then you could say, oh, there's some overlap between them, so I'm not going to reject the null hypothesis. And that would be wrong. As appealing as it is, just because there's overlap in your confidence intervals doesn't mean that the means aren't different. So it means that somewhere on your plausible range there's some overlap. So if you know sample 1 was an underestimate and sample 2 was an overestimate, then you know they're both consistent with some smaller range of the population mean. But taking the two of them together, it can still be evidence that there's a difference in the means. Or to think of it another way, you would have to, in order to get two sample means like this, or two confidence intervals like this, there has to be a fairly extreme difference in the means. And the correct way to test whether there is a difference in the means is by building a single confidence interval on the difference in means. Is that clear? Do you believe me that this approach would be wrong? Yeah, could anyone explain to me how, explain to me why that doesn't, why this seems wrong? Yeah.
Because someone could just go by looks and say the overlap part that the means are both common in that area too, so you just automatically assume the overlap that it's going to be equal at some point over there. Like you say, looks can be deceiving.
Yeah, the incorrect approach would be to just look at the overlap in two different confidence intervals. And I guess you could also think of it by saying that oh, we have a comment from online. Just like the astronaut going into space for a year, he has a twin that is staying on Earth so he can study the effect. Yeah, that's a good example of a paired observations. Okay, but what I can tell you is that in order to get confidence intervals to be completely separate, like this, there has to be a much larger difference in the means than you need in order to see the confidence interval on the difference not include the 0. So just because your two confidence intervals look like this, you might still reject the null hypothesis. All right. Okay, here's another example. This time a proper, oh yes, question.
Yeah, why wouldn't you just automatically not reject the null hypothesis in that case? Because even if there's overlap, they're not the same.
So looking at,
like, aren't we only rejecting the null hypothesis
we reject the null hypothesis if we have evidence that the means or the proportions are not equal, right? But it's evidence that they're not equal even when there's some inequality that will come just from sampling variation. So it means, because you'll always observe some difference in the means or proportions just because of the random sampling. But the question is whether the magnitude of the difference we see is more than you expect to see due to sampling variation.
It could be that those two covered intervals are slightly different, and you would still accept the null hypothesis.
Yeah, if you take two samples, your confidence intervals will probably never be exactly the same. You always get some sampling variation. But it's if the means are sufficiently different that you get a large test statistic, or your confidence interval on the difference does not include 0, that you reject the null hypothesis of no difference. Okay, so here's another example of the degree of addiction that teenagers form to nicotine using a checklist that is summarized to form a single score, this hooked on nicotine checklist, or the honk score, where a high score means you're more addicted to nicotine, low score is you are less addicted. Here is a summary of 150 females and 182 males, smokers, and the results of this score showing the average score and the standard deviation estimated from each of these samples. So this is a classic two-sample hypothesis test. We have two independent samples, and we have something that we can estimate the mean and the standard deviation for. It's a continuous variable. So we could test a hypothesis to answer the question, is the degree of addiction that teenagers form to nicotine different for males or females? So just to show the slight alteration that has to be made from the one sample to the two samples statistic, this is what we did before 2 weeks ago for the one sample t-test. You took the sample mean minus the mean under your null hypothesis and divided that by your standard error to get your test statistic, your sample t statistic. And then compared it to the t distribution under the null hypothesis with n-1 degrees of freedom. Everyone remember that? All right. Now, going to two samples, look at this. It's like almost the same again. So instead of just x bar, it's the difference between the two sample means minus the difference in population means under the null hypothesis. And this would often be 0. Often our null hypothesis is that mu1 equals mu2. In this case, the null hypothesis is that there's no difference in the sample means, right? And then you divide by this sum of two standard error-like things, the square root. Instead of just s over square root of 1, you're doing this sum of s1 squared over n plus s2 squared over n in the square root. And this degrees of freedom is just a safe estimate. If you use your software, it's a bit complicated how to calculate your degrees of freedom. So if you happen to be doing it by hand, this is just an easy way to estimate your degrees of freedom. This is with unpooled standard deviation. If one of your samples is very small, or they're both very small, and you believe that probably the variability in the two groups is about the same, then you can pool the standard deviations. So you estimate the standard deviation in each of the samples and average those standard deviations together, weighted by the sample size, and you assume the same standard deviation in both groups. This is an option when you do the test in SPSS, whether to use a pooled standard deviation or not. The pooled method is also sometimes called Welch's t-test. And you have a non-integer number of degrees of freedom, which is kind of weird. In general, if you have a large sample size, you might as well just not do the pooling because you get a good estimate of the standard deviations for each of the groups. So in this case, I would not recommend using a pooled standard deviation. Yes? Oh, Welch's t-test is another name for a t-test with pooled standard deviations. I forget what SPSS calls it, if they call it pooled or if they call it Welch's. Okay, so in this case, the null hypothesis is going to be that there's no difference in the two means, so no difference in the honk score between boys and girls. We're going to choose a t-statistic for independent samples here. And then go ahead and calculate it using the formula for the different unpooled standard deviations. So we're using the two different standard deviations here to get a t-statistic. We're going to take the smaller number sample size for this conservative degrees of freedom, look up the critical value of t in the table of t-statistics, and we get at the 95% confidence level, the closest thing we have in this table is 100 degrees of freedom. So is the critical value of the statistic going to be larger or smaller than this 1.984 if we were able to get it for 149? So you'll notice that as we go from 1 degree of freedom, the critical value is 31, up to an infinite number, it's down to, oh sorry, looking at the wrong table, 12.7 to 1.96, which is what we had for Z. So for a very large sample size, the t distribution is the same as the Z distribution. And this critical value gets larger and larger for smaller sample sizes. So to be extra conservative, that is to be sure that you won't reject the null hypothesis unless it's definitely false, you could use a smaller number of degrees of freedom. So using 100 is safe. And since our t-statistic 3.3 is greater than the critical value, what do? We reject, right? We say that the mean scores is different for boys and girls. And we could also build a confidence interval. So the middle of our confidence interval is the difference between the boys and girls scores, 1.2, so 2.8 minus 1.6. And we build the confidence interval using that formula for the standard error times the critical t-value. So 1.2 plus or minus the margin of error of 0.7. And just quickly here, we can use that. We can use confidence interval just as easily as we can use the hypothesis test to come to the same conclusion that the means are different because this confidence interval doesn't include 0, right? So the assumptions of this t-test, independent samples, yes. Normally distributed, probably not, because for For one of the groups, let's see, I don't know why I wrote one, but we have, for both of them, the standard deviation is greater than the mean. So if they were normally distributed, we would have negative values for the honk score, which don't exist. So most likely this is a skewed distribution because it can only go down to 0, but it can go up to fairly high values. So that normal assumption probably does not hold here, but this is a large sample size, 150, 182. So the t-test is going to be quite robust, and I'm not worried about it. So again, if you have sample sizes greater to 30, the t methods are very robust to deviations from normality in the population. Okay, I have another example. We're getting a little bit short on time, but I think I have time to go through this. Does cell phone use impaired driving reaction times? So here's an imaginary experiment where students use a driving simulator machine, and we have two groups. So we've got 32 students who are randomly assigned to a group where they're going to be talking on the cell phone, and another 32 to a control group who are not talking on the cell phone. So that's clearly independent samples, right? They're not paired. And we want to compare the mean response time. So in doing a 2-sample test, the question is going to be, is the average response time different depending on whether you're talking on your phone or not? So if we have response times of 585 and 533 in the cell phone and in the control group, which would look something like this box plot. So the mean is a little bit higher in the cell phone than the control group. There's plenty of overlap, like there are some very, there are some pretty slow people in the control group and some pretty fast people in the cell phone group, but our hypothesis tests are about the average. It's not the individuals that matter, it's the average. Yeah.
In this case, too, the control group too, it's the people who are driving without the cell phone?
Yeah, control group is the people driving without a cell phone. We could, so based on these averages, and actually I didn't put in standard deviations, so you couldn't actually calculate this t statistic. If you had the standard deviations, you could calculate this t statistic and get the p-value, which is less than 0.05. So you can see based on these that even if there is plenty of overlap in the population, there can be a difference in the means. And we would reject the null hypothesis and say that there's evidence that using the cell phone increases the mean response time in this experiment. Just as a side note, there is an outlier there. It would be worth checking it again with removing that outlier. There was one person in the cell phone group who didn't notice the light until several blocks later. But with a sample size of 32, I doubt that that's going to affect the analysis too much. So let's think about a different way to do the experiment. Suppose that instead we just took 32 people, or say we took our same 64 people, and with each of them, we had them do the driving test twice, once using a cell phone and once without using a cell phone. So that becomes a paired samples test, right? You're going to look at the difference in response time for each individual when they're using the phone and when they're not using the phone. So some advantages to doing your test this way, your experiment this way, is that you're controlling for the differences that occur between individuals' reactions times that are not due to cell phone usage. And you're just looking at how it impacts each individual. So you might be able to do this same test with only 32 people instead of 64 and save a bunch of extra time and money in recruiting those individuals by using the paired test. And so if you did it this way, you would record their reaction times with and without, and then take the differences. And you would do a one sample test on these differences against the null hypothesis that that difference is 0. This is the basic method. For each matched pair, you calculate this difference d, so the time, reaction time when you're using the cell phone and the reaction time when you're not. And then you use your one sample methods on those differences. That's all there is to it. Any questions about the paired test? Oh. Emily, what about an R? What's the pooled standard deviation? In R, there's also an option. If you do $t.test, there's an option var.equal, I think, equals true or false. So it's just an option to the test, just like an SPSS. And email me or ask me during lab if you want some more specific help. Okay, so just quickly, you see that in the paired test, the null hypothesis looks like it did for the one sample test. It's just that the average difference is 0, an alternative that the average difference is not 0. I'm going to gloss through these. It's just like all of the single sample tests that you've done from that point on. You calculate the t statistic just using the mean minus the mean under the null hypothesis, which is 0, divided by your standard error, and use your table of t statistics, and build a confidence interval on the difference. And the interpretation of this confidence interval, anyone want to hazard a guess? This confidence interval, 32 and 70. How do you interpret this confidence interval? So this is for the paired test.
The difference between the two sample means over 95% confidence is going to be within those two.
Or it's the change in reaction time of individuals due to using a cell phone. So our 95% confidence interval for how much the cell phone changes an individual's driving reaction time is between 32 and 70 milliseconds. Okay, and the box plot that you would show in the paired test would just be a single box plot for the differences rather than the 2 box plots. So it's like a single sample test. Okay, this is just a table for your future reference to help you decide when you have 2 samples, which test to use. If you have paired samples and continuous outcomes, such as reaction time, then you take the differences and use the T or the Z methods. We're not covering what to do in proportions. There are some other tests for so-called difference of differences for individuals. But for independent samples, it's either your T or Z 2 sample tests or using the Z test for for a single sample, or using the Z method that we just covered today for proportions. And here's one slide just to emphasize again that correct way to use the equivalence between hypothesis testing and confidence intervals, and the incorrect way. So under the correct way, we build a 95% confidence interval on the difference in the two means. And if that includes 0 or some other null hypothesis, if it includes it, then we don't reject. If it doesn't include it, then we reject. The incorrect way to do it would be by building 2 separate one-sample confidence intervals. And that wraps up the material for today. Are there any questions about this before we head down to lab?